we ended with learning the different molecular geometries that come from the different types of molecules in the VSEPR theory. So what you're going to do now is you're going to apply that knowledge. Now I know because of the snow days and everything, you're going to be reaching back for it. So we'll do the first one together, and then you'll do the second one on your own. Okay? So a few reminders about VSEPR theory before we do those practice problems. Okay? In the simplified formula, B can also be used to represent a single atom or a group of similar atoms or even different atoms in the same molecule. So I want you to look at these, right? We have, AB5, and in our version of AB5, the B's are all chlorines, right? But they wouldn't have to just be a single atom. They could be a group of atoms, or they could be different atoms. Okay, so you could have different atoms around the phosphorus, or you could have groups of atoms around the phosphorus, okay? But no matter what you do, no matter what those B groups are, the same geometries are going to form because it's the same group, it's the same number of groups, okay? You just have to remember that different sizes of B groups can distort the bond angle. So if one of those chlorines got replaced with a much bigger atom, it would change the bond angles for all of the other chlorines because it would repel more. Or if one of those chlorines got replaced with a group of atoms with a different molecule, it would obviously also alter the bond shape just a little bit, that angle, okay? You'll also notice that unshared electron pairs or lone pairs are going to distort bond angles too, and that's simply because they repel electrons more strongly than electrons that are already bonded in a pair, like in a bond. So when we had that water molecule that had 2 hydrogens and then 2 lone pairs, it distorts that tetrahedral bond because those 2 lone pairs push much more strongly. Okay. In VSEPR theory, we consider double and triple bonds the same way. So just because something has 2 single bonds and a double bond doesn't mean that that bond takes up more space. Okay? We treat it the same as if it was 3 single bonds around that center atom. Okay? We'll talk about later how double and single and triple bonds have a little bit less flexibility, but for right now, in VSEPR theory, we treat them the same. Just remember, you always need to consider all electron pairs represented in an ion or molecule. So they also treat polyatomic ions the same way they would treat a normal molecule. So just because, if you remember, a polyatomic ion is a covalently bonded group of atoms that then has a charge at the end of it. So just because the molecule ends up with a charge doesn't mean its geometry is going to be any different than a molecule that didn't end with a charge. If it has the same number of groups, it will have the same shape. Just remember to consider all electron pairs present in an ion or molecule, shared or unshared. All right, now we can try one. So to start off, we're going to draw a Lewis structure. That's the first place we're starting. Okay, so for hydrogen bromide, you have hydrogen, which has 1 electron, and bromine, which has 7. Then we're going to arrange them next to each other, which in this case is relatively simple. And we're going to give them a bond. Yay. Now we're going to check and see if each group has 8. Hydrogen has 2, which is its version of 8 because it only needs 2 to fill that outer shell. And then bromine is going to need an additional 3 lone pairs.
It doesn't have to be high. It doesn't have to be HBr. Can it be BRH?
It could be BRH, yep. Wouldn't matter what order you put them in here, so long as you have the correct number of pairs. Now, we started over here with a total of 8 valence electrons, and when we count up over here, we still only have 8 valence electrons, so there's no need for any double or triple bonds, okay? Now, we're going to call this an AB molecule. Now, why am I not calling this an ABE3 molecule? Because there are 3 lone pairs shown in this picture, right? The reason I'm not calling this an ABE3 molecule is because there is no central molecule here, and we only count those lone pairs when they're on the center molecule. When you have 2 atoms, the only option for molecular geometry is what? Linear. Okay? So this is linear. Why did I draw an M? Linear. Okay? This is a linear molecule. So those lone pairs are not on the central atom, and they can't change the fact that this is going to be a straight 180-degree bond. All right. Now, I want you to try the next one on your own. They want you to do the shape of a phosphite ion, which is PO3 negative. So this is a polyatomic ion. I will remind you that for polyatomic ions, when you're drawing the Lewis structure, total up your initial valence electrons and then add 1 because it's going to end with a negative charge. So it will have 1 extra electron. So count up how many electrons you start with at the beginning and add an additional 1 on there. Then draw your structure and try and make it match up. Okay, so you should have your phosphorus, which has 5 valence electrons. And then your oxygen atom, which should have 6. Okay. So in total, because you have 3 oxygen atoms, you wind up with 23 valence electrons. But because it's going to wind up being a negative polyatomic ion, we will instead change that to 24 valence electrons. That's how many we should have at the end. So if we then put our phosphorus in the middle and our oxygens around it, and we give them single bonds, we'll discover that the phosphorus needs a lone pair, and then each of the oxygens need 3 lone pairs in order to come out correct for the number of valence electrons to be 8 on each atom. And if we count up in total here, you'll find that we have how many valence electrons right now? 26, and we should only have 24, which tells us that we need to get rid of 2 of these electrons, and we can do that by sharing 1 more pair of electrons between the phosphorus ion atom and the oxygen atom. So instead, we can just make these disappear and connect a bond here and have a double bond instead. So this is an AB3 molecule. 1 central atom surrounded by 3 atoms. There is a double bond, but again, that doesn't matter for VSEPR theory. So what should be the shape of this atom? If you look at your chart, for an AB3 molecule, you should have a what type? Trigonal planar. It's hard to say, but trigonal planar. You should have a trigonal planar molecular geometry. These 3 should form themselves into an equilateral triangle around the center atom with bond angles of 120 degrees. They should be a triangle in a flat plane, which is why we call it trigonal planar.
How do we know that the AB3?
So, we get the AB3 by finding out we have 1 central atom, which we represent with the singular A, and then 3 exterior atoms, which we represent with the B3. So putting them into their Lewis structure helps us determine, do we have a central atom? And if we do, how many atoms are surrounding it? So that helps us here.
And lone pairs.
Yep, and figuring out if we have lone pairs or not. Which in this case we don't, but If there was a lone pair, then it would form a different shape. Good questions. Okay, that takes us to the end of VSEPR and into our next theory for molecular bonding. Okay. So the VSEPR theory focuses primarily on molecular geometry. There is another theory that, while it still gives us molecular geometry, also helps explain interactions between orbitals, and that is the hybridization theory. Hybridization is when two or more atomic orbitals of similar energies on the same atom mix to produce a new hybrid atomic orbitals that are of equal energies. This theory accounts for the ways that actual orbitals interact with each other, because anytime you have atoms bonding together, the electrons in their orbitals are going to interact, and that means those orbitals are going to interact. Okay? Consider methane. Methane is one carbon atom with 4 hydrogen atoms bonded to it. Okay? If you look at orbital notation, so this is taking you back to electron configuration, if you look at the orbital notation for carbon, you'll notice that it has 4 valence electrons. You will also notice that 2 of those are in the 2s orbital. There's only one of those orbitals. And then 2 of those are in the 2p orbitals. So it has 2 p orbitals that each have 1 electron in it, and then it has 1 empty p orbital. Okay? This is the configuration right there, the orbital notation for it, right? So the 1s is full, but it's in inner shell, so we're not dealing with it. The 2s has 2 electrons in that single orbital, and then there are 3 p orbitals, and only 2 of them have electrons in them. From experimenting, so from running experiments, we know that methane forms a tetrahedral bond. So it's going to make this shape. We know that from running experiments and actually measuring it. Okay? And VSEPR theory also suggests that because it's an AB4 molecule, that it should form this tetrahedral shape. Okay? But there's a problem. Okay? How can it form 4 equal bonds and make this shape if 2 of its electrons are in a different sublevel? Okay? Because in order for it to form this shape, all 4 of these bonds need to be equal in energy. But the 2s orbital is lower in energy than the 2p orbital. So if it was bonding just strictly that way, this shape wouldn't occur. So something has to happen. And what happens is called hybridization. To achieve this, carbon's orbitals, it has that one singular 2s orbital, and then it has the 3 2p orbitals. One of them's empty and 2 of them have electrons in it. They combine to form 4 new identical orbitals. And each of those orbitals are given a new name called an sp3 orbital. It's named after how many of each type went into it. So 1 s orbital and 3 p orbitals gets you sp3. Okay. There's 4 orbitals, and because carbon has 4 valence electrons, each orbital is occupied by 1 electron, and it can form now 4 single bonds that are all equal in energy. They have the same energy, and that energy is greater than the 2s, but less than the 2p. So the example I gave earlier was if you took a jar of spicy mayonnaise and a jar of regular mayonnaise and you mixed them together in a bowl, the resulting mayonnaise would be less spicy than the spicy mayonnaise, but more spicy than the plain mayonnaise, right? You're familiar with the idea of a hybrid, something that is combined, right? A hybrid car can run on gas or electricity. Okay? So it's a combination of things. In this case, combining orbitals to come up with orbitals that all have the same energy so that those bonds can be equal. And we call them hybrid orbitals. The number of orbitals produced is always going to equal the number of orbitals combined. So in this case, we had the 2s orbital, there's only 1 of those, and the 2p orbitals, there are 3 of those. So when we combine them together, we wind up with 4 hybrid orbitals. We won't wind up with 3, and we won't wind up with 5. We will always get 4, because we combined 4. Hybridization explains more than just the bonding for methane. It also explains the bonding for many molecules formed by group 15 and 16 elements. So, for example, we just talked about sp3 hybridization with a carbon atom, but nitrogen also forms sp3 hybridized orbitals. It takes those 3 p orbitals and combines them with the 1 s orbital. But if you remember, nitrogen has 5 valence electrons, not 4. So all 3 of its p orbitals have an electron in them already. So what happens is when you combine those 3 and then the full s orbital, you wind up with still 4 sp3 orbitals, but one of those sp3 orbitals is already full. And that results as nitrogen's lone pair. And then nitrogen is able to bond with 3 other molecules, which means because it has 3 other molecules and a lone pair, it usually forms that trigonal pyramidal shape. You have 1 orbital with a pair of electrons in it, and 3 orbitals with unpaired electrons. Each unpaired electron is capable of forming a single bond, so nitrogen tends to form 3 bonds. Do we need a second to write that down? No? Okay. What about sp hybridization? Because that can happen, right? Well, you can take just 1 s orbital and 1 p orbital and combine them together, and you'll end up with 2 sp orbitals, which will yield you with a linear geometry. A good example of that is beryllium fluoride. Okay, it takes beryllium's 1 s orbital and the 1 available p orbital that's empty in beryllium, and then combines them. Okay. And sp2 hybridization is going to give you 3 orbitals, because you're going to take 1 s orbital and 2 p orbitals and combine them together. Example of that would be, gotta remember, boron fluoride, 1 singly occupied p orbital and 1 empty p orbital, sp2 hybrid orbitals. And then sp3 hybridization, as we discussed earlier, yields 4 orbitals, which means that it can form that tetrahedral geometry, or if one of those orbitals is full or 2 of those orbitals are full, then you get different geometries based on having those be full. So remember, when lone pairs are involved, they can affect your geometry. So why care about molecular geometry? Well, we care about it because it affects intermolecular forces. Intermolecular forces are forces of attraction that happen between molecules. So we have discussed the forces that cause attraction inside of a molecule, right? We know the reasons why hydrogen atoms bond with oxygen atoms to form water. But when you make a molecule of water, there will also be forces of attraction between the different molecules of water in a sample of water. So not only are there forces inside the molecule, but there are forces between 2 molecules that are next to each other. Generally, these forces that are between molecules are weaker than the forces holding the molecules together. And how strong your intermolecular forces are is going to affect physical properties of your substance. One of the most obvious is going to be the boiling point of a substance. The stronger the forces between molecules are, the higher the boiling point of that substance. The only real difference between something being a solid, a liquid, or a gas is how close together its particles are packed. and how easily they move around each other. In a gas, particles are very spread out, they're not super attracted to each other, and they move freely and independently from each other. In a liquid, they move freely around each other, but they don't spread out apart from each other as easily. They're not as independent. And in a solid, they're very close together and very strongly attracted to each other, and so they form rigid shapes. The intermolecular forces are what are causing those attractions between the particles that keep them in a solid, in a liquid, or in a gas. So the stronger those forces are, the more energy you're going to have to put into a substance in order to break those intermolecular forces and therefore allow them to change state. One of the strongest intermolecular forces is the force of polarity. If you remember when we discussed polarity, it's that differences in electronegativity in atoms cause one part of a molecule to have a partial positive charge and one to have a partial negative charge. Orbitals and molecular geometry help determine molecular polarity because the shape of a molecule will also affect whether or not it's polar. Differences in electronegativity cause bonds that are formed to be polar, and they can create what we call dipoles. A dipole is an equal but opposite charge that's separated by a short distance. So when you have that small molecule that has one end that's partially positive and one end that's partially negative, you wind up with a dipole. Dipoles point from the positive pole to the negative pole. So if I was going to draw one, and let's say I had a molecule here, right, and this end was partially positive and this end was partially negative, I would draw the dipole like this. Okay, the little plus is going to be on the positive side and the arrow is going to be pointing towards the negative end of the molecule. So we represent dipoles with those little arrows. So the shape matters because knowing the orientation of these dipoles in the geometry of an atom will help you determine if the molecule is polar or not. Because these dipoles, if they're all pointing in the same direction, will add up, but if they're pointing in different directions, they can actually subtract from each other and cause a molecule to not be polar. In a diatomic molecule, where it's just two atoms, polarity is only determined by one bond. So, for example, if you have one atom bonded to another atom, and this atom is much more electronegative, then it's going to pull on the electrons and be partially negative, and this side's going to be partially positive, and as a result, you will have a dipole that points this direction, because there's only one bond here. But if there are more complex atoms, those dipoles can add up and cancel each other out. So for example, I want you to notice that in the water molecule, both dipoles are pointing towards the oxygen, which means the negative is over here and the positives are on the hydrogens. And because they're both pointing in the same direction, this molecule will in fact be polar, because these dipoles will essentially combine to make the oxygen be partially negative and the hydrogens be partially positive. But in the carbon dioxide example that's on the right, even though oxygen is very electronegative and carbon is not so electronegative, because these dipoles are pointing in opposite directions to each other, we're going to wind up subtracting them off, and you're not going to see this molecule be polar. This will in fact be non-polar. If we just looked at the formula of this and ignored molecular geometry, it'd be very easy to assume that carbon dioxide is a polar molecule, because oxygen is very electronegative and carbon is not. So it would make sense logically from that to conclude that this would be polar. But when you combine that information with the knowledge of molecular geometry, you get a more complete picture. And now we understand why molecular geometry is so important. The negative region of one polar molecule also attracts the positive region in adjacent molecules. We call this a dipole-dipole force. So what's happening is you have your polar molecules, okay? They're in a substance together, and they're going to have their partial positive and partial negative charges on them. And this partial positive is going to be very weakly attracted to this partial negative over here. I don't know if you can see my little drawing there, okay? Lots of little dots trying to symbolize a attraction between that positive and that negative there. Okay? And that's what we call a dipole-dipole force. It's one of the stronger intermolecular forces, but it's still weak compared to the forces inside the molecule. Polar molecules can even induce dipoles in nonpolar molecules by temporarily attracting their electrons. These forces are weaker than dipole-dipole forces. So what you're having happen here is you have a polar molecule that's got a positive end and a negative end, and then you have a non-polar molecule over here that doesn't have a charge on it. And what happens is the electrons from over here are pulled towards this positive charge, and then we do wind up with a little positive and negative charges forming on this, and then they're attracted to each other. This is temporary and it's weak, but it can happen. Hydrogen bonding is a type of dipole-dipole force. So what we just described happening when you have polar molecules together. But it's stronger than just regular dipole-dipole forces because it involves hydrogen. So when you have compounds where hydrogen, which is a very much not electronegative, bonded with very strong electronegative atoms like oxygen and fluorine and nitrogen, the hydrogen atom gets a very strong positive charge because those electrons are being pulled away from it very strongly. Its positive charge, in fact, is almost half a proton's worth of positive charge, which doesn't sound like a lot, but remember, we're talking about very small things here, so having a positive charge of almost half a proton is a pretty significantly strong positive charge on this hydrogen. The other factor is that hydrogen atoms are very, very small, which means they can get very close to unshared pairs of electrons that are on molecules near to them. So, what happens is the hydrogen atom is bonded to that highly electronegative atom. So then it gets that very strong partial positive charge, and then it's attracted to the unshared pair of electrons that are on that atom, the electronegative atom in the nearby molecule. Let me illustrate using water. You get a molecule of water, which is an oxygen bonded to two hydrogens. And oxygen has actually two lone pairs sticking off of it, right? And what happens is another molecule of water will be nearby because they're all together. And this hydrogen is going to form a very temporary bond with this lone pair that's on the water molecule next to it, on the oxygen. And that'll happen over and over again in sort of just a repeating pattern. And as a result, all of these water molecules are bonded together with relatively strong forces, which is why, even though water is a covalent molecule, which generally speaking have very low melting points, right, winds up having a much higher one because of these intramolecular forces. So its boiling point, melting point increase because of the intermolecular forces. So still not as high as a ionic compound, but much higher than standard covalent compounds. Hydrogen molecules also serve a purpose in helping stabilize the structure of your DNA. Your DNA is made up of lots of different molecules, and those molecules individually pretty weak, but when you add all of those hydrogen bonds in, it really helps strengthen up the structure of your DNA so it doesn't fall apart, which is, pretty important for life. Let's talk about the last intermolecular force, which is London dispersion forces. London dispersion forces are the weakest of the intramolecular forces, but they are also the most common. In fact, they happen in all compounds, all molecules, even ones formed between noble gases. So those don't tend to form lots of bonds, right? But even in those compounds, London dispersion forces are present. And here's how they work. Electrons around all atoms are constantly in motion. Think like hummingbirds, how they very rarely sit still, right? Your electrons are even busier than hummingbirds. They never stop moving. They're moving all the time. And as a result, at any given instant, electron distribution could be slightly uneven. So because these electrons are not moving together and they're not moving predictably, they can all wind up on the same side of an atom at the same time just by happenstance. Think of it as if you were sloshing a bucket of water, that water is going to slosh heavily to one side, right? The same thing can happen on an atom, but it's just because those atoms are moving and they all wind up around that spot at the same time. And what happens then is that those electrons being there very temporarily gives that side of the atom a negative charge and the other side a positive charge because it has less electrons over there. And so it creates a very, very weak and very temporary dipole on your atom. And then just like dipoles can cause temporary dipoles on non-polar atoms, this temporary dipole caused by moving electrons can induce a temporary dipole on another molecule, and then those atoms will be held together by that weak temporary attraction. London dispersion forces increase with increases in atomic or molar mass, and that's because as you increase the mass, you're going to increase the number of electrons, and when you have more electrons moving around, then there can be more electrons that end up on one side, causing a stronger negative charge, which would mean a stronger temporary dipole, and so on and so forth.